hello to everyone on YouTube who rather went to the parade than come to class. I should have given you all the exam solutions before, just to you can screw them. I mean, I did. I told you all of the answers. We haven't designed your second midterm yet, so if you want anything on it or off it, now's your time to sort of tell me what you want.
Easy.
Can we tell you what we don't want instead?
What don't you want?
A hard test.
Okay,
No optimization.
Can't do. That's like the point of calculus,
okay.
right? Well, what would you rather do? I could give you some really tough. Like, I could make this a tough test that like doesn't test concepts at all. I could give you really hard chain rule problems, right?
I know.
What chain rule is easy to fucking optimize? I'd rather get a really hard.
It's easy until someone, he has the right idea.
What?
Well, just tell me what you want, what you don't want, and I'll see what I can do. I can't not give you an optimization question that is like the point
Can you
of
make it
calculus.
like one question, not worth a lot of marks?
For what?
The optimization.
Or can
So
you make
really
it-
what you want to do is get a good mark on this, yeah?
Yeah.
Okay, but I'm telling you how to get a good mark.
Oh,
Can you put a
yeah.
bonus question?
Can you put a bonus question?
Okay, but the bonus question could be just hard.
basically
No, no, you
impossible.
can make it really hard if you want.
Yeah, then like half of you will spend like waste 20 minutes trying to solve the bonus.
How is a bonus true or false?
Bonus true or false? I'm not going to give you.
50-50 chance of like.
All right, well, you screwed your chance because you're not taking this seriously. I would have. Okay, well, tell me, what do you want? Like, what's the weak point here?
Where did people do the worst
Inverse
in the
trig.
test?
Can we not do
If I was
inverse
like
trig?
Well, the first test was the first, like last year, the first test had like a 30% average.
Oh.
So you guys killed that. I think it's basically because we failed you all on your quiz first. Because last year, the first feedback they got was midterm 1. And the feedback was, you got to do better than this. Right? So this year, we're like, we better give them something that's not worth a lot to tell them that signal. To say, you have to do better than this.
Okay,
Right.
so sorry, the last year the average was 30%?
Yes, for the first midterm.
Oh,
So we are treating you. I am already making it easier than it was during the year.
Could we have like a practice midterm review? No, what, no, not the review.
We'll try to do your
test.
practice midterm again.
test again.
You guys gonna do it this time? Because like,
Yeah,
this
we
is
did,
very
we
similar,
did it the
right?
last time,
Well,
I think.
not many, right?
Oh.
Huh?
Inverse trig.
Inverse trig? You want that on it?
No, I don't.
No.
Okay.
Would it be possible to do like a very similar question from the quiz to have on there? Like the
You're just
same
gonna try to
question
memorize
for
it, though.
something?
Yeah, that's true.
Well, that's the.
And then I'm gonna start you
Make
halfway
a
through and you won't get it. I'll put
Can
like a
you
little
not
spin
do
on it
that
and you won't be
thing?
able to do it, huh?
Can you not do the thing where you're like, oh, do this at 1? Like, like on the quiz, you're like f of 1. Like,
No, I'm definitely gonna do that. Got to get used to working with like function abstraction. All right, well, I'll take this all into consideration. Okay, so y'all got your paper out? Okay, so I'm going to give you maybe like a minute or so. I have 48 slides, so we got about 30 seconds to try it and then a minute to do it. So here's your first one. What is going on? I have the wrong tool here. Let's just go out of this. Okay, so what I want you to do is determine if this is basically like the first section from the midterm test. So determine if the statement is true or false, and if it's false, you should provide a counterexample. I guess that should say provide a counterexample if false. Well, provide a counterexample when appropriate, I suppose. If f is a function, then f of s plus t is equal to f of s plus f of t. Is that true or is that false? You stop doing the thing I told you. Don't say the answer out loud, right? Write it down on the paper. Huh? Yeah. Well, that's why I'm not going to put the answers on the slides, because I'm afraid people will try to memorize them. Memorization is not a viable strategy in this course. I'm going to design it so that it's not a viable strategy.
Just saying, like, I got it wrong the first time.
Yeah.
So when I saw the answer, I'm like, oh.
Fair enough. But give me a counterexample then. Yeah.
So you're not gonna put the answers on the slides, but we're gonna take it up.
Yep.
So the people who missed this wouldn't know the answer.
Well, it's being recorded. And it's also their prerogative to miss classes. It's not up to me to make up for the fact that they've skipped something. Okay, if f of s is equal to f of t, then it's necessarily the case that s is equal to t. Counterexample if false. Hello. If f is a function, then f of 3 times x is necessarily 3 times f of x. Tell me if I'm going through these things too quickly.
Yeah.
Yes. Geez, okay. These slides are already online. It's being recorded, so don't feel like you have to copy down the questions. Just I probably should have numbered them. There's a number here. So why don't we just say this is question 5? Yeah.
Is there going to be office hours?
Yeah, I'll do office hours today.
During the break?
Email me, and then we can meet if you want. I'm going to be here Monday, Wednesdays, and Fridays because I use the gym, so those are the best days to get me. If x naught is less than x1 and f is decreasing, then it's necessarily the case that f of x naught is strictly larger than f of x1. Okay. A vertical line intersects the graph of a function at most once. Eight. If f and g are functions, then f composite g is the same as g composite f.
Is this a review for like past midterm?
Yep. Yeah. And don't be surprised if some of these appear on your midterm.
Okay, so,
But don't try to memorize the answers because I'm going to change them a tad, right?
so it is like cumulative sign.
It's always, I can't teach, like, it's always cumulative. Always. Because I can't not use the first half of the course in the second half of the course. It's all dependent. This is all a dependent chain of inferences.
But I mean, like, in terms of, like, the true and false questions, like, it's not going to be strictly to, like, let's say the theories and examples from what we've been covering.
No, it's always cumulative, right? Mostly because I don't want you to think you can then drop all the stuff we learned in the first semester. All right. If f is a one-to-one function, then f inverse of x is 1 over f of x. Ten. You can always divide by e to the power of x. $11. If a is strictly greater than 0 and strictly less than b, then that must be the case that ln of a is strictly less than ln of b. Question 12. If x is strictly greater than 0 and a is strictly greater than 1, then ln of x over ln of a is equal to ln x divided by a. $13. The arctangent, or inverse tan, of -1 is 3 pi quarter. Question 14. arctan of x is equal to arcsine of x over arccos of x. If the limit of x goes to 5 of f of x is 2, and the limit of x goes to 5 on g of x is 0, then the limit of x goes to 5 of the quotient f of x over g of x does not exist.
Is this on the Quarkus right now?
Maybe. Oh, the slides?
Yeah.
Yeah. Oh, sorry. Okay, this is already chapter 2, so I think I went one too far. So, okay, so that was function. So let's go back to the beginning. And now we can get all rowdy again while you tell me what the answers are. Okay. So what's the answer to this? It's false. Why? Yes, sir.
You can use x squared as an example for the function, and let's go with points 2 and 1.
Yeah. Okay. So sorry, YouTube, you're not going to see solutions today. Well, I think that's great. Yeah. So don't choose x. X is too simple. That's the identity. So maybe you say x squared. So if we have f is x squared, this means that f of s plus t is s plus t squared, which is s squared plus 2st plus t squared, which is not equal to s squared plus t squared. We call that the freshman's dream, actually. This identity. Because it's not true. It's a very widely made error.
Where on Quarkus is it? Is it under?
Oh, sorry, it's on Piazza. I haven't put it on Quarkus yet. Yeah. There's an iOS app for Piazza and an Android one, and it's quite good.
I use it all the time.
Mhm. That's why I like Piazza over Quarkus, because there's a phone app. If f of s is equal to f of t, then s is equal to t. Another way of reading this is saying, look, the only way for a function to attain the same y value twice, or this is basically saying it's impossible for a function to obtain a y value twice. Right? So obviously, this is not the case. Here's x squared. If this is s and this is t, there you go. You found two places. So this is false because of x squared. If f is a function, then f of 3x is equal to 3 of f of x. Also false, right? I think this also will work for the parabola. So if I make the parabola, if I let f equals x squared, f of 3x then would be 9x squared on the left-hand side. On the right-hand side, you'd have 3x squared. And 9x squared is not equal to 3x. So the parabola seems to be a good counterexample, although something simpler would just be a line with anything that's like minus x would work here, I think. No, bad. 2x, I think, would also work, like a line with slope 2. So again, this one was false. Okay, if x naught is less than x1, so we could just go ahead and, so I just sort of, if you are troubled by this, you can just sort of draw as you go, right? So you have x naught, and you have x1, x naught is less than x1. If f is decreasing, so we have to have a decreasing function, that means the function has to be going down. This means that f of x naught, this one, has to be bigger than f of x1. So is it that, if this is a decreasing function, should it be that this point is higher than that point? Then this is true. A vertical line intersects the graph of a function at most once. True or false? True. Why?
So it's a function, then it comes to the vertical.
Yeah, passing the vertical line test is the definition of what being a function is. So this is basically saying, does a function pass a vertical line test? Yes, by definition. So that's true. If f and g are functions, then f composite g is equal to g composite f. False. Can anyone give me a simple example?
3x plus 7 is f, and 4x squared plus 5 is g.
3x squared, 3x plus 7 is f, and g is what?
4x squared plus 5.
That'll probably work. Can we, like, what's the simplest one that we can get? Can we get something more simple than this?
X plus 1, x squared.
X plus 1 and x squared? Let's try that. So you should always try to get these more sophisticated examples or worse. You want the most simple thing that breaks it, right? Getting something like this isn't better necessarily. Well, it's not better. This is simpler, and if it works, would be better. Okay, so what's f of g of x? F of g of x here is x squared plus 1. And then g of f of x, which is x plus 1, would be x plus 1 squared. Right, so there's going to be a 2x term here that's not present in there. So good example. Yours worked too. I just didn't want to work through the arithmetic. If f is a one-to-one function, then f inverse is equal to 1 over f of x. True. False. False. Because that -1 doesn't mean 1 over. Right? That's the notation for the inverse, which is different than inverting.
So invert would be f of x to the power of -1.
Well, let's just try to find. Oh yeah. So if you actually wanted to get the reciprocal, you'd have to write this. The magic of brackets. Okay, so let's pick two. Can someone give me a function? So let's try f is equal to 2x. It may not work. What's the inverse function here? Okay, so 1 over f of x. Okay, so if f takes x and goes to 2x, then f inverse should take x and go to half x. Right, it's clear if you take the composition of this and this, you get 1. Right? Okay, so thereby I found the correct inverse. So is it the case that, right? So 1 over f would be 1 over 2x. And this is 1/2 x. So there's a real example where those two things aren't equal. But this is basically saying, do you understand what this notation is? Right, because otherwise, well, that's what the trick is. So don't get confused by the notation. If we put a -1 on a function, that indicates inverse. You can always divide by e to the x. True or false? True. Why? Okay, when are you not allowed to divide by something? When it's 0. Is e to the x ever 0? Well, it's e to the x. So e is 2.7. E to the x is like a variety of values, none of which are 0. Right? So it's always, e to the x is always strictly greater than 0. It can never attain 0, thereby you can always divide by it. So that is true. If a is in between 0 and b, so I'm just going to write down our data as we're working with it. Okay, so what do we got? We have a graph. We have a, which is bigger than 0, but less than b. Right, so you can just sort of draw the information you have as you're going. So ln of a looks like this, or sorry, ln of x looks like this. So here's ln of a, here's ln of b. I suppose ln of x is a strictly increasing function. So if a is between 0 and b, is it the case that this point is lower than this point? Yes, this is true. If x is greater than 0 and a is greater than 1, so I guess I can just change this to an x. Then ln of x divided by ln of a is ln x over a. I don't even think, is this true or false? It's false.
Shouldn't it be subtract?
Like we can very clearly, yeah, so for one, the rule should be subtraction. But consider this. What's ln of 1? 0. So if I make x equals 1, this obviously doesn't work. Because the left-hand side is 0, and the right-hand side is non-zero. Only ln of 1 is 0, right? So the other side is going to be ln of 1 over something that's, like, I suppose a could be 1 is, oh no, a is greater than 1. So I can't make the right-hand side ln of 1. So there you go. If you set x equals 1, left-hand side becomes 0, right-hand side is never 0. Right, so you don't have to overwork this. It's like we're not asking you to prove these things, which would be a hell of a lot of extra work. All right, so it's good enough to just answer correctly the true or false status. Is this true? Well, how do you work it out then? Right, so what is arctan? Right, so we need the triangle whose ratio of opposite over adjacent gives us -1, right? So we probably need, so opposite over adjacent, I think maybe we're in here, right? If this is +1 and this is -1, then, well, that doesn't seem right. What should this angle be then?
Should be -1.
Well, what's the 1, 1, √2 triangle have inside of it?
Pi over 4.
Yeah. Well, I drew the angle in there, so we can still say that this is pi quarters. But the actual, in this instance, we actually need this angle, because that's how we do trig. We always have to do that, the outside angle, not the inside one.
Can't you say -pi/4?
Right. So what's -pi/4 though? Standardized in the 0 to 2 pi region. Well, what's this angle?
7 pi over 4.
So the whole thing is 2 pi.
Yeah.
So that's going to be 8 pi quarter, 7 pi quarter, 3 pi quarter. Yeah, so I think this should be
Yeah, because 8 pi.
7 pi quarter. Okay, so I think the arctan of -1 should be 7 quarter pi.
Wait, so how would,
Opposite over adjacent, yeah. Huh?
so how would it be different if it was just tan -1?
What totally changes the question, right? So you have to give me an angle when we're working with tan.
The tan -1 equals that true or false? Like
It's
how-
false, obviously false, right?
How did you incorporate the arc into this?
Yes, that's what I was going to answer.
Because we're recovering an angle from the sides of the triangle, rather than recovering the angle, the sides of the triangle from the angle. So are we forgetting our trig, right? So opposite, adjacent, hypotenuse, right? So remember, like these values, the sine theta, cos theta, tan theta, these are all just ratios here. So you can either give me the ratio to retrieve the angle or the angle to retrieve the ratio. The inverse tans are saying, here's the ratio of the sides, give me the angle back.
Oh, so, okay.
Arctan is ratio to angle, right? Tan is angle to ratio.
Okay.
Okay. Okay. Maybe we won't be scared of arctan. Okay, I have to check this. I'm not actually sure, right? Well, at least I'm being honest with you. Because I could have drawn, like, I suppose another way I could have drawn it was,
in the other quadrant.
yeah, I could have drawn it here.
And since it's opposite over adjacent, the -1 could be in the denominator too. It would still
Yeah,
be-
it could be -1 here and 1 here.
And it could still be negative, and that is 3 over 4.
3 pi quarter.
So it is true.
I think, it's true. It could be, it's.
I was-
So do we have to take-
Well, you shouldn't be confused because we're going to get an infinite amount of solutions for all of these problems.
Yeah.
Right? There's going to be, like, sine and tan go like this. You get one solution, you get an infinite amount of solutions. Right? So, like, it may be, like, both of these is correct. So, let me just check. 0.785. What's 3 times pi quarter? All right, no, let's do it like this. Actually, all we have to do is take the angle and go backwards. So what's tan of 3 pi over 4? -1. Okay, so it's true. Yeah. So be careful, yeah, these do get tricky, right? Because I had 2 options for drawing the triangle, I needed to do both. Yes, miss?
Is it possible, like, to draw arctan and then realize that the boundaries are between pi over 2 and negative pi over 2? So 3 pi over 5 would be outside of the boundary. When it comes to -1, it would be a negative value.
So -1's going to be here.
So can you think that 3 pi over 4 is a positive point, which couldn't work? Is this
So the problem is this is arctan standardized for in here only. Like remember that tan looks like this. So like this is only arctan for this guy, the one centered at 0. There's going to be like more arctan functions for each one of those you choose. So like one of the answers to this question is we could say it doesn't exist because of the funny way that we defined it. But the fact of the matter is if you take 3/4 pi and plug that into tan, you get -1 back. And so that has to be, so like there's other answers to this question where we can get really technical and say the point that you're asking for is actually outside the natural domain of the arctan. But that's not as like, you can get a solution. So that's the one that I would prefer. But this is why tan's tricky, where you got to try, like, you get multiple correct answers, right? And you sort of have to think, did I find all of them properly? Yeah.
I was gonna ask, like, if there's a true or false question and there's multiple answers and you just give one, like, is it fully true? Because there's more than one answer.
Well, I can rephrase it like this. Well, I don't know. You would have a case here to say, look, our textbook defines this point as outside the natural domain. It should have been false technically. So maybe sometimes I'll do. If I'm wrong when I give you a true/false question, I'm more than happy to give
Just
it.
like be more specific. Like there are multiple possible solutions, for example.
Can we
Like,
not
if
get a
you're-
question where there's
Can we-
multiple solutions?
Well, this question is basically saying,
Is
is
it
tan of
like
3/4 pi
absolute?
-1? And the answer to that is true.
Yeah, but it's saying it's like it's absolutely it can't be anything else.
I'll try to make, I won't put very ambiguous questions on your midterm. And if they do appear, I will give you the marks for them if I've introduced ambiguity. But like, designing tests are hard. Like, yes, I'd much rather write 100 tests than the design one. Right? I don't, like, you'd think I just go into the textbook and pick 5 or 6 random questions. No, we have to put a hell of a lot of thought into this, right? To make it at the right level, to make sure we're hitting the learning objectives, right? To make sure that the people who are memorizing are going to be screwed, right? Like, I am telling you that we do that on purpose, right? Memorization does not work. Okay, so we got to look at our trig a little bit harder then.
Okay,
Yeah.
sorry. So can we just make the true and false questions where we're not spending so much time on the question? Because I feel like a question like this, you probably spend some time trying to figure it out.
Well, you should be experts at trig, right? Like that's all you did in high school.
No.
Well, how much trig did you do in high school? Like all of your grade 9 and 10 basically should have been trig. And then that should have been re-emphasized throughout the rest of your career. Right?
I don't remember 9 and 10, but 11 and 12.
Okay, let's move on. I won't put a ton of trig on this. Like this is just from this test is going to be more tilted towards like the 3rd chapter and 4th chapter. So let's get there. This is false, right? It's obviously false. Okay. So do you want to just like do the question and talk about the answer instead of like, do you want to repeat what we did for the 1st chapter or just go straight to like talking about the answers? Let's go straight, yeah, because I'm not sure we'll get through it all if we don't. Okay, so what about this one? If the limit on f to 5 goes to 2 and the limit of x goes to 5 on g is 0, then does this limit exist or not? Well, I think nothing's going to save you from generating an asymptote at 5. Right? So at best, you can get like 2 positive infinities. But I think in all cases, you're going to get. If I could somehow make f also 0, then we could play some L'Hopital rules tricks. But they're specifically saying f goes to 2 at 5. So you have something which is definitely 2, and you're dividing by something which is definitely 0. So you definitely generate an asymptote. So this is true. Okay, so if the limit of x goes to 6 on a product of 2 functions, if that exists, then, okay, well, this is a nonsense question. I think what I meant to say is that if the limit of x goes to 6 on the product exists, then the individual limits also exist. Right? The limit of x goes to 6 on f exists, and the limit as x goes to 6 on g exists. Is that the case? Right? If the limit of the quotient exists, then the limit of the individual functions exists.
You could separate the 2 terms inside, right? Like limit of f and then limit of g.
Well, that's what I'm trying to go for.
I mean, like, you can literally take it out.
So it's basically like if the limit of x goes to 6 of this exists, then this exists. X goes to 6 of f, and this also exists.
I have a question about the previous question. Can't you simplify that to limit as x approaches 5 f of x minus limit as x approaches 5 g of x?
Minus?
Am I mistaken?
Minus? How do you get a minus?
Can't you simplify it like that or no?
I think you're thinking of what we're doing when we have lawns.
Oh,
Yeah.
probably doing that.
Yeah. Any guesses here?
Sure.
So like what I'm thinking in my head is what happens if you have f and then you have g and their product give you 1. Or you have f and then like the reciprocal of f.
Oh.
You get 1. So that's a function which is the constant function. It's everywhere defined. Everywhere has a nice limit.
You're trying to prove this wrong.
I'm trying to prove it wrong. Yeah, what happens if you have a pole? We can have like 1 over x minus 6. Okay, so let's look at it like this.
Oh, and then that would create a...
And that would create a pole, but I can get rid of it by multiplying it out.
A fold?
Like an asymptote.
Oh, okay.
Yeah. Sorry, that's borrowing notation from complex analysis. Okay, so if I have 1 over x minus 6, that doesn't have a limit as x goes to 6, right? That generates a pole.
That's just f of x.
But if I multiply this by x minus 6, it becomes 1. And it's everywhere defined. So if I let this be f and I let this be g,
And then g is the inverse of f.
yeah, basically. But I made it so that g doesn't have a limit at 6. But the product does have a limit. So this
it's
is
still
false.
true. Oh, this is false.
Yeah. Well, I didn't write the question down correctly. It's the false for that guy.
Isn't that a really
So,
good question?
could you write it where it's like, where how you would have written it?
That's that.
Okay, right there.
Yeah.
It's just, for this specific example, it's true, but in general, it's false.
No, this is not
False?
false. This is false because this is a statement about every single function.
Okay.
So as soon as you find one function that doesn't satisfy it, it's false.
So sorry. What you wrote right there is so right there, right? So it'd be limit of x as it goes to 6.
Well, I can try to change it, but I think you think that these slides are done a little bit differently than you may expect. I can change it. I'll fix it. Where is it? Whoops. I can't fix it. I have some. I'll fix it. I'll re-upload it on the website correctly when I get back. Okay. If P is a polynomial, then it is the case that x goes to B on P of x is P of B. Any guesses?
Yes.
I say true, right? Because we're obsessed with polynomials because they're so nicely behaved. Right? Polynomials are everywhere defined. They're functions, right? So yes. Because more or less, in order to get the limit to not exist, you need to divide by something. And as soon as you start dividing by something, you cease being a polynomial. So this is true. If limit of x goes to 0 on f of x is infinity, and limit of x goes to 0 on g of x is infinity, then their difference is 0. No. Well, this is an indeterminate form. Right? Infinity minus infinity is not 0. It could be 0. I'm not excluding that as a possibility. For instance, if f and g were the same function, this would be true. Right? But it's not true for every function. Right? So when you're looking at these questions, you're not asking if you can find f and g that work. You're asking if you can find f and g that breaks it. Make sense? Right. Infinity minus infinity is indeterminable. And that's infinity minus infinity is not 0. Is why this is false. A function can have two different horizontal asymptotes.
True.
Anyone agree? Yeah, you can have one asymptote for positive infinity and a different one for negative infinity, so this is true. If the domain of a function goes from 0 inclusive to infinity and has no horizontal asymptotes, then the limit as x goes to infinity has to be positive infinity or negative infinity. Another way of phrasing this question, what's the alternative to limiting to like a horizontal asymptote? You're either limiting to something constant or infinite.
So,
True. Yeah. But does everyone see my reasoning there? A horizontal asymptote means that your function's approaching something finite. And the only option to not approaching something finite is going infinite. Right? So that really is the other one. Yes, miss?
Go back to the other question. So, like, what's the most that you can get?
Of 2. For horizontal asymptotes, you can have 2.
And vertical?
You can have an infinite amount of vertical asymptotes.
Okay.
10 has an infinite amount of vertical asymptotes. Yeah. If x equals 1 is a vertical asymptote of y equals f of x, then 1 is not in the domain of f.
Did we just skip one?
Did we?
What about 20? No, never mind.
This is, 21. If x equals 1 is a vertical asymptote of y equals f of x, then 1 is not in the domain of f.
true.
True, false, maybe,
True.
both. I say true. This is basically saying you have like a pole, an asymptote. Right? So where the function is approaching but never attaining. If f of 1 is greater than 0 and f of 3 is less than 0, strictly in both cases, then there is a number c in the interval 1 to 3 such that f of c is 0.
No, because it doesn't say the function is continuous or. Yeah, so.
Oh, for you! Because I was going to say, of course, this is the intermediate value theorem. But they didn't give you enough information to actually assert that you could use it. So your answer's better, actually. I was going to answer this wrong. Right, so, okay, so the wrong end, like the trap of this question is it's saying, look, doesn't this look like intermediate value theorem? But the answer is we haven't paid the toll yet. We have not yet established that f is differentiable and continuous over that domain. Good for you. I'm giving you some extra marks. See, right there. Writing it down. No, but that actually does make me proud, because I was going to get this wrong. If f is continuous at 5, and f of 5 is 2, and f of 4 is 3, then the limit of x goes to 2 of f of 4x squared minus 11 is 2. So maybe give this one some thought. I'm going to go try to look at this one from the back of the room, gain a different perspective.
If you just substitute for bx, so 660 minus 11, which is 5, f of 5 equals 2.
So let's take.
What's the trick?
The first thing we should always try is the five.
Well, yeah, but can we plug it into the...
What happens if we do 2 5? 2 squared is 4.
But 4x squared minus 11.
We're actually asking us.
I mean, that's just...
Can we get efficient functions of this? Where we give this?
First thing you should always try is evaluate. Once you do that, you say they're just asking if f is 5. And you also need to remember that you're allowed to take f out. You can apply the function second. Right? We wanted to be real technical about this. It's one of the limit laws, right? Remember we established limits and I showed, look, we can add them and multiply them and apply functions. So if you were in a math course, I'd say true, but prove it. You'd have to say, well, look, I can take the f out. That's a rule. The inside is the limit of a polynomial, so that's free. And then I can apply f after. That's the reasoning. That would be the reasoning. And so if we took out applications from calculus, then I'd have to put back in, like everything you answer, I'd have to say prove it. Prove it, right? Not just state it. Okay, what do you guys get? True or false? I assume thumbs up mean true? Okay. Double thumbs up is true. Anyone watch Futurama in here? How do you plead? Beep, beep. Double guilty. There's 1 beep for guilty, 2 beeps for non-guilty. You beep twice. Double guilty.
That was
Okay.
Zap Browning episode,
Valua. Okay, if f is continuous, so basically what happens, what's the first thing that we should try to do when evaluating a limit? Plug in the value. So what do we get if you plug in 2? 4 times 4 is 16, minus 11 is 5. So they're basically asking you the question, is f of 5 2? Yes. True. F of 4 is a red herring. B, yeah, so we that's the other way we can trick you. Is give you an extra piece of information which is like redundant or useless. All right, so B, you guys know what a red herring is?
Yeah, I know what it is. I just know where it comes from.
Oh, the term?
Yeah.
Well, I don't know. I assume it's something to do with fish, right?
Fish?
Isn't a herring a fish?
Isn't that a bird?
Wait, is a herring a bird or a fish?
I don't know.
A herring is a fish. A heron is a bird.
What is a bird?
H-E-O-R.
Oh.
H-E-R-O.
All right, this is why I'm not teaching you biology. I don't know the difference between birds and fish, right? If f is continuous on -1 to 1, there's a missing closed brace there. And f of -1 is 4, and f of 1 is 3, then there is a number r such that the magnitude of r is strictly less than 1, and f of r is pi.
But pi is... f of r equals pi. But pi...
Pi is a red herring.
Pi
Pi is a number. Pi is a number like any other number.
That's what I'm thinking. Is it in the domain? Like,
Pi is a fish or
R
a bird.
is what we're referring to the domain, right? Is pi between...
No, pi has nothing to do with the domain. Pi is the target. Pi is a range target.
Yeah.
Yeah.
R is what deals with the domain.
R is dealing with the domain. Yeah. But anything in negative 1 to 1 is going to have absolute value strictly less than 1.
That's true. Wait, I'm according to.
Okay, so this continues.
You know what? Maybe I'll turn this into a real question. One. Yes, intermediate value theorem. We have no slopes here. We don't need mean value.
Because intermediate value function states that if it goes from here to here and it's continuous, the
We're
value
going to get all the values in between.
Well, it's gonna hit it. It's all the values in between.
What, negative 1 and 1, or 3 and 4?
3 and 4. It's the range. It's the range.
So that's true.
And but again, pi is distracted. Right? Don't automatically think trig. It's just like
3.14.
I know, but I'm trying to get you guys over this hump of treating these special numbers as extra special. Okay, so what do we settle on? True or false? You think true? Who's willing to bet a percentage of their grade?
That is true.
I already told you. Okay, but how do you prove it? How do you prove it? What piece of technology are we using? Yes. Intermediate value theorem, because in this case, we do have f is continuous, which is what we were lacking in the last time. So remember, intermediate value theorem is not only a piece of technology that gets you through 0. Right? It will get you through 0 if the function is above 0 and below 0. But this is a function that's below 4 and above 3. So intermediate value theorem in this case says you're going to hit all the values between 3 and 4. And pi just happens to be a value in between 3 and 4. Right? So don't get tricked when you see a pi. Don't automatically think that we need to start doing trig. Yeah, I thought we were bonding a little bit.
I wasn't going to say it.
When you lecture, you sort of have to pick 2 or 3 people, right? At least that's why I like you, because you nod occasionally. Even if I'm talking about bullshit, you're like, yeah. All right, let's go. If f of x is greater than 1 strictly for all x, and the limit of x goes to 0 if f of x exists, then the limit of x to 0 of f of x is strictly greater than 1. Doesn't this remind you of last year?
For all.
The eye clickers?
Yeah, no, that's true, because it says for all. X is
Like,
approaching
don't put
0.
data on there. Like, fuck it up.
And x can be anything. Then rules.
Don't put data.
0 is in the domain of everything. Oh, yeah, true. Easy peasy. Like f of 0 is greater than 1 for all x, and for 0 is in the domain of everything. I want a Subway sandwich so bad. Let me ask you. I'm like legitimate. Let him answer this one question. Well, I mean, let's just finish this.
5-minute break after this.
Yeah, can we take a break now?
You want a break? Sure. Well, why don't we take a break after we get to the break point? Let me see how many more we have.
We have like 1, 2, 3, 4, maybe 3 more.
Okay, so let's try to do these next 2 or 3 real quickly so I can give you a break. So what's the answer to this one? If f of x is always bigger than 1, and the limit of x goes to 0 exists, no. You can limit to 1.
I'm sorry.
You can limit to 1.
What?
How?
You can make the limit to 1, but since it's not saying it's equal to 1, it's for all of them. Can the elements bigger than?
Here's a horizontal asymptote. Call it y equals 1. Here's a function which is approaching it. Oh, I guess it always has to be bigger than 1. Okay, so I have to do this one. But that's a function that's always bigger than 1. That's limiting to 1. Remember, limits never actually obtain the value that they're limiting for. This one was kind of tricky. But it's a good learning. It's a good learning. Maybe I'll put this one on the test. I like it.
Yeah, do that.
Sure. It's false. False. Or maybe I'll switch it so the answer changes.
Oh my God.
Just so you don't memorize, right? Just don't memorize. Well, do memorize the stuff that you're supposed to memorize. Like, that always surprises me. Yeah, triangles, for example. You need to memorize all the trig identities. Okay, did everyone understand that explanation, or should I go over it again?
I don't know.
We gotta
Wait, I have a question. It's limiting to 1, but it never touches 1, so it's technically always greater than 1.
No, but the limit itself is 1, equal to 1.
So it could be
So
like,
will the limit always be 1 or can it be greater than 1?
Well, no, this is first. Okay, let's talk about this again. Okay, so maybe I'll try to come up with a honest to God example.
yeah, exactly.
But basically, okay, so what we got to do, here's the horizontal asymptote y is equal to 1. I just got to find any function that's going to do this. So I believe 1 over x plus 1. What's the limit of x goes to infinity here?
Well, that one's right.
Oh, 0, 0. Okay, I'm going to have to shift this.
It still works. You just don't.
Also approaching 0.
That's approaching 0.
I can get, hold on, but can we approach it 0 to 1?
So we have to think about it geometrically.
I somehow have to make the limit to 0 1. It's easier to do it with a horizontal asymptote, but
So why can't you just move to the left?
What's
It's above 1 for all x.
because I'd have to shift this leftward by an infinite. I have to shift it leftward infinitely much to get its limit to 0.
Robert, can we just change it back to infinity?
True.
Can we just say that that was the question? Like, that's
Oh, if I make x go to infinity, then yeah, this would be the answer.
Okay. But will
I don't
they-
know actually. If it goes 0, I have to think about it.
If f at x is always greater than 1, then
For all x.
if you're approaching 0, then
You have to
it's,
leave it.
then
It's
true.
the limit of the function.
Yes.
Right? Not the function itself. So I understand that the function is strictly greater than 1. But that's a function that's strictly greater than 1 can still limit to 1. Right? The limit is equal to 1.
But it can also be greater than 1 if it was a different function. right?
Yes, but again, we're searching for any
Okay.
function that breaks it. Not trying to find a function
So
that
if it said
confirms.
greater than or equal to, like that would be fine. Less than or equal to.
Like we keep changing every time you make a change to the problem, we're going to have to readdress the whole thing from scratch. It's not like I can say if this is a greater than or equal than, then we do this. It's like, no, like for this question, we have to take it as one thing. If you start changing things, then we have to consider it all over again. Because it fundamentally changes what they're asking. Okay, so with an infinity, it's false. For 0,
Wouldn't this still
You have to
be
shift this function.
even on that example, it's still approaching something that's bigger than 1.
no, but it's not. It's saying approaching at 0. I don't get to pick the limit point. They're giving me the limit point.
So you have to shift that
Even in this
function.
one, it says approaches 0, it's still
As
bigger
it
than 1.
approaches
Any
0.
value is still bigger than 1.
Yeah, that's confirming it. As I approach 0, I'm going to infinity.
But that's not true in this.
Well, yeah.
Yeah, but I'm trying to break it. I was trying to come up with an example which would show that it was false. Because look, here's a function which is everywhere greater than 1, which still nonetheless limits to 1. But that limit was infinite. They're saying this limit is at 0, and now I'm trying to figure out if I can somehow position this so we're limiting to 1 at 0.
If you move the vertical asymptote on the negative value, wouldn't the whole thing shift?
I'd have to shift it leftward by an infinite amount.
So if I said like 1 over x plus.
No, I can't. I can't say 1 over x minus infinity. That's not a function.
You can say 1 over x minus 100,000.
Anyways, I'm going to have to think about this a bit more. My feeling is that it's false. I should be able to contrive some type of example which...
There's no, you don't have an answer key?
Answer key? No.
It's a question. When you made the.
What if the answer key is wrong? The answer key is made by graduate students. I can find, in the answer key, there's at least 100 mistakes. There's mistakes in your book. There are tons of mistakes in your books. Yes! This is not Bibles that we're handing over to you. This is the solution keys are designed by the graduate students. We're the least reliable. Yeah.
Yeah, if you split the curve
If I flip it, then it violates the first condition of it being strictly greater than 1.
The function is always, the function is always greater than 1.
Also, just because I can write down a question doesn't mean the answer even exists. I can give you lots of questions which are well defined, whose answer is impossible to determine. Right? I'm gonna have to think about this. But think. Maybe this will be the bonus question on your test. You asked for it.
But you
Right?
don't even know the answer to it.
I sometimes have to think about these things. Like this is. I told you at the very beginning of this class, I'm not perfect by any means. I'm going to be making tons of mistakes, right? The same as you, arithmetic, conceptual.
So what if you don't find the exception to that, even though there is one, and then?
Well, I have to sit down and try to prove it. I'm going to try to come up with a proof that says it is true, and then at that point, I will say that it's true. I would just like to sit down and try to prove it before I make a definitive statement, right? Because if something's true in math, you can demonstrate that it's true. So if I can demonstrate it, then I'm going to say to myself, okay, yes, now I'm sure, right? Yeah.
Once you do figure it out and work through it, could you post it online?
I'll post it online, but the proof may be well
I'd be
above.
interested in-
Yeah, no, I'm thinking I can design it, but it may be, I don't know. Okay, if f is continuous at a, then f is differentiable at a. False. Give me an example.
The absolute value.
Yeah. Corners aren't, you can't differentiate corners. Right, so continuity definitely doesn't imply differentiability. Yeah. If f prime of r exists, if the derivative of r exists, then the limit of x goes to r of f of x is f of r. Okay, so what did we say the derivative of something like this was? Do we have a derivative there or not? Because technically the secants exist. Like you can get, oh no, that has to be filled in. I think we do have a continuity requirement.
Wait, to be differentiable, it has to be continuous at every point, right? No, because like if there's a hole, there's a limit of the hole, that limit exists, but below that value, it doesn't.
Right, this we're going to have to look up the definition in the book, right? What does the definition in the book say?
Of what?
If the limit, basically I can't remember how we defined it. We can do it either way, right? Like if I have a function like this with a point removed, did we say that has a derivative or not?
Well, it has to be continuous, differentiable, and the limit from left to right is 80. That's the definition.
No, we can't have the definition. We can't. Continuity can't be a requirement for tangents because you have a circular dependency there, right? So the definition here was that the left and right limit secants have to exist. But I guess if you're connecting,
No, as it approaches it, it has to be that value.
that's what the definition of continuity is. Right? They're asking us if the function, they're saying in order to have a tangent on a curve, the curve has to be defined. Right, so that really depends how we define it. So flux, I'll post the answers to these. I think I've changed my mind. I will update this with answers on the thing with some explanations. Yes.
You don't have to move it infinitely to the left. To 100 to the left.
And what did you get?
I got as x equals 0.
It's not something. You can get it. 1.01.
It's approaching 1.
Oh no, at infinity. At infinity, it's approaching
0.
No, at 0, I can tell you it's at 0. It's approaching 1.01. Right. Anyways. Okay, go take a break. You guys can think about this one as you have a break. But it's basically just another application of IVT. Please make it quick. Yeah. The other reason I didn't do the answers before is because if I can't get it, then there's no way in hell I'll do it. If I can't solve a question in like 3 or 4 minutes, it's not an appropriate question for an intern.
We can make this. We can make an example. If it's 0, no, but if the limit has x equals 0, if f would have made it half at x equals 1, then the limit has x equals 0. If this point said 0, 1, then
Professor,
Professor, if I magically made this point 0, 1, then it would be true.
Yeah,
Okay, hold on. I think maybe. What about this? What about this? I think that would work.
Oh! It's 1.
It's not really.
It's 1.
And the number is so small.
I think that works.
It's 1. Look.
It's not.
I plugged this. Oh my god.
You don't understand a limit,
The
man.
number is so small, it's showing one. It's not one.
Yeah, that's different.
They're not going to choose 60.
Look at us.
You probably won't change your mark that much.
That's
Right? It's only like, it's only 1%.
Yeah, I think that's the answer. You can get to 1 and then remove the circle. I think I figured it out for that other one. This is a function which is defined like it's everywhere bigger than 1, and its limit at 0 is 1. It's just not continuous there. Right? The limit goes to 1.
Is it differentiable there?
No, was that one of the
Yeah,
conditions?
that's not good fun. Otherwise it'd be easy. It said f of r has to be differentiable. Yes.
No, I'm talking about this one, question 25. The one that he's arguing about. Right? It doesn't even make sense. Yeah. It's a nonsense statement.
But he solved it. So that has to be in a normal. Oh, that's great. There's a hole in the acid zone. Bruh. There's a hole.
So if you find a mistake in a book, let's say it's like I have a standard one up to and like all the mistakes I found in the book. Jesus convey on his authority to do this for and like solutions are bad. Because if you give them to the graduate students to do, like the mainline material is written by
LQD invented, they're not only
every book I've ever has tons of mistakes. It's impossible to do mathematics error free. Because like not only are you, because there's like multiple things that are happening. You're doing the math, and then you have to type it into a computer. And that process itself is going to introduce errors. And like, I don't have a buddy. No one's like going over my notes. That's you guys. Hoping you guys will find some mistakes.
Oh, no, because I had the idea, I thought like you had made up these questions.
Yeah, but even then, I could have had the wrong idea. But just because you define the question doesn't mean you're going to answer it.
Is that a prop just like
No.
remake the entire course?
No. This is a standard way of presenting this. But like when I work on the board, I'm doing it genuinely. It's not like I memorized the lecture. It's like, here's the questions I'm going to do. Like the day before, I worked at 2 years. Sometimes I got stopped a whole. When I'm doing it for you, I'm trying to do it in such a way but I'm speaking out what I'm thinking. So you can see what I'm thinking. That's what really doesn't work. I have to help you guys sort of how to think about those tests.
Oh yeah.
Like I can give you very free lectures. Those are so boring. Because I just do slides. And then you do it on error free. And it's going to be very, very boring. I like the fact that you guys can catch on. It means reading. And it's showing you not to do that, like how to correct things. Right? So like I do it on purpose. I make mistakes. Like I'm trying to not make mistakes, but I put myself in a position to make mistakes on purpose. Because it makes it more interesting and you learn. Yeah, you should not treat books as life, because I could show you heaps and heaps of instances where they're outright wrong.
Why would I
look at this. The slides come out of this. Mathematicians have to use this language to explain to the computer how to typeset.
Just use PowerPoint.
Take one of, like, take. No, it makes it 1,000 times harder. That's why we had to invent this language.
That's why.
Well, have you ever tried putting equations into and having them align, cross-referencing equations and stuff like that? That's what we invented this in order to.
What is this?
It's a language called LaTeX. So that produces something like this, right? So I can say.
How do you know if it's like, okay, we're going to check this user is active?
Oops.
Are you in a program right now? Like,
See that piece on the right? Generates this picture.
you can even add it to your paper, right?
I used to like going up. I used to have to look how to like find.
What do you choose?
Yes. So you went from Windows to Mac.
I'm supposed to be, but yeah,
That's how I. That's the definition of computer science. Actually, researching online and seeing how someone else did it. But I just want to give you an impression why mistakes can show up, because we don't see the output. We're reading off this essentially. Hmm?
Got all those characters. There was one that looked at back in his P of double line.
I've heard, yeah, the first midterm, so many.
Not ampersand, it's just the end of line character. When you start programming, things like blanks and new lines are relevant. So those are on, like, those are hidden characters that are there, but not drawn by the computer. Like, it's not physically drawing a blank, but in mind, I do draw a blank. Okay, let's continue. If f and g are differentiable functions, then it is the case that the derivative of the sum of the functions is equal to the derivatives of the individual functions summed.
What was the last one?
Yeah, this is true.
All right, does anyone have an answer for this?
Oh, that one. True.
It is true.
Does it go through the, well, let's just plot it. If it goes through the axis, then it does. What was it? X squared. No, it wasn't x squared. It was like x to 100. Oh, x10 minus 10x squared plus what? Where's 0 and 2? Yeah, okay, so there's 2, there's 0. It actually goes through the axis twice. Right? Of course, you should have tried to search for some values where this was positive and negative. But this confirms it. Okay? So it does have one root at least. Okay, but this was the big problem on the practice midterm, right? Like when we set you up IVT, like I'm not like giving you perfectly chosen boundaries, right? You have to search for the points. If we're nice, we'll give you boundary points that work, but it's not really how you use the piece of technology. Okay, how about this one? This one, like true or false?
It was true, right?
True, yeah. But why it's true is more important. Right? Like, I should be able to say, prove this now with IVT. Is this true or false? The derivative of a sum of two polynomials, the derivative of a sum of two functions is equal to the individual. Yeah, that's just, yeah. Don't overthink it. What about this one? The derivative of a product of two functions is equal to the derivative of the products. No, what rule do we need here? Product rule. The derivative of f of g of x is f prime g of x times g prime of x. What is it? What is this? Chain rule. If f is differentiable, then the derivative of the square root of f of x is equal to f prime of x over 2 root f of x. This fills me with joy seeing all of you argue and like do this, and fills me with joy.
I get a chain rule, but no, here.
What's the derivative of square root x? 1 over 2 root x. X to the 1 half. Half comes down. 2 in the denominator.
Oh, yeah. Okay.
Should try writing on paper perhaps. This is true. It's true, right? If y is e squared, then y prime is 2e. No. What is it really?
It's just, it's 0.
0. E to the squared is just a number. Derivatives of constants are always 0. Constants have no change. You got tricked. Yeah. But be careful, right? Because you don't want to lose the easier marks, so to speak. The derivative of ln 10 is 1 over 10. No. Why? It's a number. Because it's a number. Maybe I will put this one on the test.
Yeah.
Just to throw you a freebie. But if you get it wrong, I'm going to cry myself to sleep. If f and g are differentiable, then the derivative... What? That doesn't make any sense now, does it? Okay, just ignore the first line. The derivative of tan squared x is equal to the derivative of secant squared x. False. It's a trick. It's a trick.
It's a trig?
Can you write me an expression that includes tan squared and secant squared? What's the relationship? Isn't secant squared 1 plus tan squared? Do I have the signs of that right? Is 1 plus tan squared secant squared? Someone confirm this? Is it? Plus. Okay. So it's true. Well, I'll write it. I think. Because the derivative of tan squared x is equal to the derivative of 1 plus secant squared x.
Does the 1 matter?
1 will go away. Right? We're taking the derivative. And you just told me that I can take derivatives over sums. So that 1 will disappear. It's true. A little bit tricky, but it's true. I wouldn't give you something like this. I think this is too tricky for... I'm trying to bolster your confidence in the true-false section. Right? Yeah, but see, this is the problem. I know all of you can understand the solution when you see the solution. So when you stop, you're like, I understand that solution, I understand the solution, I understand. But it's like, that's not what we're asking you. We're not going to give you a test saying, can you explain the solution? We're going to ask you to provide the solution. And that's a totally, you understand, it's a totally different skill set. Right? Production versus understanding. All of you can understand. Very confident in your ability to understand. But it's your ability to produce the answer you got to work on. Question or just thanking the guy above? Korean Jesus, right? The derivative of the absolute value of x squared plus x is equal to 2x plus 1 absolute value.
36, yeah.
The derivative.
Oh, slide 36. Because the slides are mine.
This one may actually need some working.
I'm actually not sure how to take the derivative of something in an absolute value.
We wrote that, didn't
Yeah,
we?
we did. I don't remember.
Who remembers what the derivative of the absolute value of f is? Well, you can work it out.
Yeah, it's like.
We worked it out. We worked out what the derivative of the absolute value of something was.
Oh,
We
yeah.
changed it to
It's like-
square root x squared, right?
Yeah, you change it to the square root of x.
That's right.
Okay, so then you guys work on this a little bit. You can work it out. I'm not going to give you the answer, right?
I remember it's like x squared over the absolute.
You work it out. Work it out. Don't try to remember it. Just try to work it out, and then you'll remember it, right? Okay, so I'm not going to render.
What?
I'm not going to tell you what the answer is here. I want you to work it out. Right? Just go ahead and work out the derivative of the absolute value of x squared plus x. Sorry, I have to kind of rush. Okay, this is all limit stuff. Okay, an equation of the tangent line to... No, that's boring. Okay, applications of differentiation. I think we can get through 10 slides. 2 minutes each. Okay. So now this is chapter 4. Right, this is the latest stuff that we've done. This is mostly the stuff that you guys don't like the related rates and the word problems. Okay, so if the derivative of a function, well, if f is flat at c, right, it has a zero slope at c, then f has a local extrema at c. No. No.
Everyone was like, yes.
Hold on.
Can you give the critical point is not necessarily a local extreme?
Can't we have a critical point that's an inflection point? Like, that's what I'm trying to get at.
Yeah. On x cubed.
So it's false.
So it's false, yeah. Right, because this shape here, that has flat slope at that point. Right, so it's not good enough to only be flat. Right, so you also have to have the correct concavity. You need some restriction on the second one, huh?
I mean, no, the inflection point isn't critical point, but it's not really it's just
Let f equal x cubed. Let c equal 0. This won't work out. Okay. If f has an absolute minimum at x equals c, then it has to be the case that there's a zero slope there.
Yes.
yeah.
Think harder.
Think harder.
Oh, it's an absolute minimum.
Absolute minimum.
Not necessarily.
Not necessarily the case because of boundary conditions. Closed interval. Here's a minimum. Does not correspond to any critical point. Okay, classify quiet. Usually
Okay.
does this.
Yeah.
Yeah, okay. Don't forget about the boundary conditions. Right? The thing that should throw you here is this absolute minimum. As soon as it's the absolute minimum or maximum, then you throw locality away. Right? This is something about the global value, right? So don't forget about boundary points.
So in these kinds of situations, we can impose certain rules on functions just in order to like.
Well, they're saying this is true for every f.
Well, for every.
So logically, you
and
can
f
give-
that's on an interval as well.
It has no, they give you no domain restrictions.
Okay.
Right? The only restrictions are f is a function and it has an absolute minimum. So that, right? So don't put extra stuff in. Right? If it's not there, it's not there. That's our fault. Right? I'm not going to say, oh, well, I meant to write that this had an infinite domain. And you said, well, you didn't write that. So as stated,
I
right?
see.
Okay.
Okay, so we can just fuck around.
If f is continuous on that interval, a through b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f at d, at some point in those two things.
Yeah.
No, the absolute minimum and maximum.
What if it was just a straight line?
Again, you found one example where it works, but we're trying to search for an example which breaks it.
I'm trying to say, this is a straight line, break it.
No, straight lines is fine. The problem here is that it's an open interval. If it was closed, then this would be true. So what can happen here is that your maximum and minimum values occur like that. And then they're not in it anymore.
But even if they were closed, couldn't it just be your other example? The one over there.
Well, if we change the question, then yes, it needs different consideration.
It would still be false though, right?
Now, if it was closed, it would be true, right?
Well, why wouldn't the endpoints be the absolute maximum and minimum? It doesn't say that I'm going to have two endpoints. It just says.
Yeah. So if I close off the interval, if I include the boundary points,
Yes.
and I let C and D be those boundary points, then this would be true.
But it's A and B that are the boundary points. Is it saying that C and D could also be A and B?
If they're included, yes. This question excludes the boundary points. And because it excludes the boundary points, this is false. If we were to include the boundary points using square brackets, then this is true. We actually have a theorem that says you're guaranteed absolute maximums and minimums on closed intervals. I forgot what the name was, but we definitely have it. Extreme value theorem or something like that? Yeah. If f is differentiable, and f of negative 1 is equal to f of 1, right? So if we run a horizontal line through, oh, actually, yeah, we'd have to run through f of 1. Then there is a number c such that the absolute value of c is less than 1, and f prime of c is 0. Mean value theorem. Try to recall it. And this is a statement. They're saying you have 2 points on your function which are at the same y. Right? So they're saying, is there some points in between those 2 points where the tangent is flat? Clearly, yeah. So by mean value theorem, this is true. Yes, sir.
Why does f be less than 1? Oh wait, never mind.
Yeah, because it has to be in between negative 1 and 1. That's just, it's a weird way of giving you a domain restriction. But it's equivalent. Yeah, sometimes someone will say that because they're too lazy to write both sides of the interval. When you're centered at 0, the absolute value becomes like a shortcut for defining intervals. If the derivative is everywhere less than 0 of the function f, for everywhere between 1 and 6, excluding the boundaries, then f has to be decreasing on that interval. Yeah. What's the first thing saying? It's saying, well, everywhere in this interval, the tangent is pointing downward. That's the definition for decreasing. So yes, this is true. If the second derivative of a function is 0 at 2, then 2f of 2 is an inflection point. Okay, so remember, inflection points is where the curvature changes, right? So you get 0, but that doesn't necessarily indicate that the curvature changes, right? So the opposite thing is true. If the curvature is changing, then the second derivative will be 0. We have that direction. We don't have the opposite direction, right? So take something like x to the power of 7, right? That's going to have, x to the power of 8. That should give you something that's super flat here. So you'll have a 0 second derivative there, but there's no change in inflection. If f prime of x is equal to g prime of x for everything in the interval 0 to 1, excluding the boundaries, then the functions have to be equal. Okay, this is saying 2 functions have the same derivative graph. Let's think of our antiderivative lecture. What did we determine? Yeah.
Antiderivative can result in multiple derivatives.
Yeah, that there's a whole family of functions that share derivatives.
So you get the plus c at the end.
Right, so x squared, f, g is x squared plus 1, They both have derivative 2x. So this is false, right? There's a function f so that the function goes through the point 1 minus 2 and 0, 3, and it's everywhere has slope greater than 1. Does that function exist? Can a function with these conditions exist? Tricky one. Be careful.
It's like a parabola, and then it goes negative.
Well, this is the only information you have. You have this point and you have this point.
No, it's telling you that the thing is always more than 1.
Yeah. Okay, you and then you. Yeah.
Okay, the slope here would be 1, but it says the slope has to be bigger than 1.
That's what it says.
Oh, so you're saying that this is false?
False.
It's false.
Yes.
Is there a function that?
Right, no, okay. So any function that has to go through these 2 points will satisfy the following condition. The slope between these 2 points is 1. You can calculate it. This is the point 3, 0. This is the point minus 1, 1 minus 2. Rise over run. 3 minus 1 is 2. 0 minus minus 2 is 2. The slope of this line is 1. That means if I were to draw a function through these 2 points, mean value theorem ensures that at some point we're going to have slope equal to 1 between those 2 points. Mean value theorem assures that. Okay, well this is impossible because I just found a point which has slope equal to 1, and this is saying that the slopes have to be strictly greater than 1. A little bit tricky, this one. Yeah. But it's a pretty straightforward application of the mean value theorem. So you should be sort of picking up that the mean value theorem is something that you better have a good hold on. Right, you'll definitely be getting a question like that. The one I expect everyone to get wrong is the mean value theorem question, right? As everyone sort of didn't do the IVT one correct. So just remember that you may have to manipulate the problem a bit to get it to where it needs to be. 8 more minutes, 2 more slides. There is a function f. Maybe we'll let you do this one. Okay, so there exists a function f, which is everywhere less than 0, that has everywhere less than 0 slope and everywhere positive concavity. And so you go home and think if you can construct such a function f. How about this one? If f and g are increasing on an interval I, then their sum is also increasing. So I'm happy. What happens if we can we find 2 functions which sum to 0 or sum to something constant?
But they both have to be.
You could still be increasing, right? Like, so the 1, 2, 3 is increasing, and negative. Oh no. So usually when I look at these things, I'm trying to find 2 functions which like delete each other. If I can get something constant, then it's no longer increasing. Remember, something constant isn't increasing. To be increasing, you really have to go up every time you go forward. Constant functions are non-decreasing and non-increasing.
Trying to eliminate like variables. There's no way to
I think this has to be true.
There can't be like a negative, like negative x squared is.
Well, again, we should introduce specific functions because we need to make it like, so this is like, this would be the other math. right? You wouldn't be given this question as a true-false statement. You'd be given this question as a demonstrate its validity, right? Prove it is true, which shouldn't be too hard, right? You just pick a couple points from F and a couple points from G, and you try to manipulate it a bit. But I have a lingering feeling that this is true. Because that's the thing. You can't say I tried really hard to find a counterexample and I couldn't, therefore it's true. And that type of argument doesn't sort of work in math. You really have to be sure. If F and G are increasing, then their product is increasing. I think this one has to be false. Hold on. Because I can have something that's everywhere increasing and negative.
That's what he said.
And then you have something positive on the top.
And then when
And you multiply them and that thing
they all
starts
become
going
negative.
down.
Yeah.
Okay, false. Yeah.
Can you say that again?
Could you,
Well,
could you provide like a concrete example?
You do it.
I suppose. Fair.
I guess if like F is X,
G is.
then I need something everywhere negative.
Negative 1 over X?
Isn't 1 over X? 1 over X is not everywhere.
What if you do X and X?
Yeah, negative 1 over X is always decreasing. Yeah, okay, so
No, but it's always in.
it's decreasing, always decreasing. 1 over X is always decreasing.
We need both of
Oh,
those.
okay, so we flip it, negative, and that becomes always increasing. So I guess if you have F and G is minus 1 over X, this is everywhere increasing, this is everywhere increasing, but their product is negative 1, which is nowhere increasing.
And it's constant.
Oh, it's constant.
Oh, yeah.
Yeah. Good job. Yes, sir.
Couldn't you also do it like false? And like this X and G of X would be X plus 1. That would be like a power of X squared at some point. Doesn't that mean that?
Oh, that's a good one as well. Yeah, okay, so if you have F is X, and we don't even need to make them different. Nothing's saying they need to be different.
X and X.
Right? If you have X and X, those are two increasing functions, but X squared isn't everywhere increasing. Oh, I don't know, that may be better than yours. But both are correct. Right? But you see how, like, yeah, that, I would say that is the most simple counterexample. But still both, great. Yes,
Do
say
you
what?
expect, to sketch
The what?
the sketch?
Oh yeah, you're gonna have to do curve sketch. Yeah. Everything that was taught you is important. Otherwise, it wouldn't show
I mean,
it.
like as a long answer, like that would be like a long answer question, right?
Usually,
Yeah, so like different parts split, then sketch the graph.
you're gonna have to utilize all of your knowledge. Curvature and maximum derivatives. Okay, everyone, have a nice holidays. I'm going to be in Monday, Wednesdays, and Fridays. Usually, if you want to see me for a little bit of consultation, be sure to have a little bit of a break. You need to let your mind rest a bit. So, but you also need to study a bit. So.
But that's not what the
Sir.